All right, in this section, 12.4, we're going to learn a new type of equation called parametric equations. And then we're going to do a little bit of calculus on those. So the way that we work with parametric equations is we still have points x and y. Only instead of y equals f of x, which is what we're used to, we totally eliminate y as a function of x. Instead, we're going to introduce a third letter or a third variable t. This is called the parameter. The parameter, hence the term parametric functions. And the way that we determine what the points are on a parametric function is that we have two sets of equations, one for x and one for y. And in these two equations, x is a function of t, the parameter, and y is a function of t, the parameter as well. So here I have an example, and I'm going to show you how a graph of a parametric equation looks. All right, so in order to do this, I just want to point out here, x is a function of t, x equals 2t. Y is also a function of t, and I've also given you an initial point for t and a final point, sort of. T is not ever equal to 2, but we're going to stop just when t equals 2. So in order to graph these, I'm going to plot points. And so we're just going to make, I guess instead of a t table, maybe you would call this an h table. And now, since x and y are both functions of t, you're going to pick values for t, because t is now the independent variable. So let's pick 0. Why don't we try 1 and 2, even though 2 is going to be an endpoint hole. So it's not really an endpoint, but it's an end hole. Okay, so when t is 0, what is x? Well, x equals 2 times t, so 2 times 0, or 0. And what about y? Well, y would equal 4 times 0 squared minus 8 times 0 plus 4. So that's 0, 4. All right, so let me go ahead and start to graph this. I have my very first point, 0, 4. All right, let's move on to when t is 1. If t is 1, x is 2, and y is 0. So now I have the point 2, 0. And then let's go ahead and do if x is, or if t is 2. So if t is 2, and again, I'm just plugging into my functions for x and y. So when t is 2, x is 4, and y is, what is that, 16 minus 16 plus 4, so that's 4. So I have the point 4, 4. And that's a hole. Okay, and then I'm just going to connect these with a curve. And another thing that happens with parametric curves is that they have a direction. And so what you want to do is you want to think of t as time. And in fact, this is how a lot of things in the real world work, is that we have parametric equations, x and y, as functions of time. And so if at the beginning, when the time is 0, I start up here at the point 0, 4, and then I travel along this curve, you can see that the direction would be along the curve pointing in this direction. Okay, but we only need one arrow. All right, and so that's as simple, that's all it is. It's very simple. So that's how you graph parametric functions or parametric curves. We also want to, with this new system of equations, we also want to be able to connect to our old system. And that's when we have the relationship between x and y only. So we want to sometimes eliminate the parameter. Eliminate the parameter. We have two strategies in order to do this. The first one is our most basic one, and what you're going to do here is solve for t in one of your equations and plug into the other. Then my second strategy is what to do if you have trig, functions. And I've shown you this for sine and cosine, but you also might have to use the Pythagorean identities for secant and tangent, and cosecant and cotangent. And the idea there is to solve for sine of theta and cosine of theta, or actually, I guess, sine of t and cosine of t. and then you square and add together and get 1. So let me show you how this is done. Over here, I have 2 examples, and this first one, notice there are no bounds on t. That just means t runs from negative infinity to infinity. What I'm going to do here to eliminate t is I'm going to solve for t and say, it doesn't matter, the first one. So then x minus 2 equals negative 3t. Divide both sides by negative 3. And t is x minus 2 over negative 3. Now I'm going to take my other equation y and replace the t with x minus 2 over negative 3. And I've successfully now eliminated my parameter. So y equals 1 plus 2x minus 4 over negative 3. And I guess that should simplify some more. Negative 2/3 x, plus 10/3. No, 7/3. And that's it. And so this is a line, and we know what that line looks like. But it will graph the same exact line that this will graph, as long as your t runs from negative infinity to infinity. All right, and now let me show you how you do this in my second example, where I'm going to have a sine and a cosine. And so it's not easy to solve one of these for t. You don't do it that way. Instead, I'm going to take the x equation, and I'm going to solve for cosine of t. And then I'm going to take the y equation and solve that one for sine of t. Now I want you to take each of these equations and square both sides. And I'm not going to even bother to FOIL this out. I'll go ahead and square 2. And then on my other one, y squared over 9. And then what I'm going to do after this is I'm just going to be tricky. I'm going to add these 2 equations together. So when I add the left sides together, I get x minus 1 squared over 4 plus y squared over 9. And that equals cosine squared of t plus sine squared of t for when I add my right sides together. And sine squared plus cosine squared, well, that is just the number 1. And so we've used a trig identity to eliminate the parameter on this one. And so this is the equation that we get in rectangular form. Notice this is not a function, but this is the graph of something you know. This is the graph of something that we just went over. What is it? What is it the graph of? Okay, you can go ahead and write down what you know that this graphs. You could even graph it probably really quickly. Okay, so now let's go the other way. Now that we know we have parametric equations, how can I take a boring old regular rectangular equation where y is a function of x and get this into parametric mode? Well, it's really, really simple and a little silly. But all you want to do is let x be t. And then once x is t, you're going to let y, you know that y will have to be 2t squared minus 1 in this case. That's it. That's all it is all there is to it. Except for there is some trickery when you get something that's one of these conic sections like we had before. Here you want to sort of recognize a pattern, and we'll go over those. We will go over those as we get to them in the homework problems. The last thing that I want to cover right now is how you find the derivative of a parametric function. It's important to know the derivative of a parametric function. Notice I have to talk about this in Leibniz notation because you want to know y prime, but what in the world is y prime now that you sometimes have y as a function of x and sometimes you have these parameters t? Well, you want to know dy dx because that is the slope of a tangent line. Dy dx is the slope of a tangent line. And the formula for what dy dx is, when you have y as a function of t and x as a function of t, these parametric equations, is to simply take the derivative of y with respect to t and the derivative of x with respect to t, and that is your dy dx. And the reason why that works is if you look at this fraction, if you were to think about dividing by this fraction dx dt, that's like multiplying by the reciprocal, and so you get dy dx. which is what we want. Okay, and so let's do 2 more examples here. On this first example, I can find dx dt. I just need to take the derivative of x, where t is the independent variable. And then I can find dy dt, and so that is just a half. And that means that dy dx is going to be dy dt, 1/2, divided by dx dt, 2t minus 3. And we're done. Now notice your dy dx, your slope of your tangent line, is a function of t, but that's okay. And then the next thing they wanted us to do was to find the slope at t equals 0. And so all I have to do here is to put in t equals 0. So m, or dy dx, evaluated when t equals 0, is 1/2 over -3, -1/6. Okay, and then we have one more example, and yes, I am going to leave this one to you. See if you can remember your derivatives of trig functions, then plug in 0 and tell me the slope.